Hey everybody, we are Capital One. My name is Timmy Liu, and we have JayZ on the right side, Nori in the middle, and Mark here behind me. So I'm an analytics manager at Capital One. I've been in the financial industry for about 10 plus years, and at Capital One for 6 of those. My focus at the company is really answering questions related to why should we invest our resources in this or that project. So today I really want to focus, spending a few minutes talking to you all about our customer servicing phone calls and what those entail. So when we think about customer phone calls, we traditionally think of them as a cost center. And we use a cost center lens where it's really focused on reducing them as well as making them more efficient. So I want to take this view of it being a cost center and kind of flip it on its head and propose that, no, there's actually a lot of value in these phone calls that we get from our customers. And it's not just a cost center that we want to remove, but rather we should pay attention to these calls. We should pay attention to these calls and the data and the voices within these calls and use them to monetize our products. Because the data within these calls are full of customer voices that tell us about our organization, about our servicing, as well as about our products. What do our customers like? What don't they like? What do they need? What do they find useless? What upsets them? And what do they get excited about? So I want to highlight today a little on why these phone calls are so important and the problems that we at Capital One faced in understanding all of these voices. So people never really wake up in the morning thinking to themselves, man, I just cannot wait to call my credit card company today and talk to a servicing agent. That's just not how the world works. So it's important to keep in mind that credit cards are never really an end product, but rather a medium that allows people to conveniently acquire the services and products that they really want, as well as a tool for managing their finances. So when the customers call us, it's usually about something that's not working with our product or something that could actually be better about our product. And so here's where the value is, right? These calls are not just a simple cost piece for us. It's a gold mine of customer voice data that provide us a feedback loop. It tells us directly what we should work on and what we should improve. And so this is why it's so important for us to research into these calls. This is why these calls are so powerful and rich with information. It helps us iterate, prototype, and improve our product servicing and experiences. So I want to talk a little bit about how we used to get insights out of these calls. We get over hundreds of millions of calls a year from our customers. And for the longest time, we were only able to get insights through very laborious and manual methods. The first one would be we just pull up a few of our associates, sit in a room, and listen to phone calls all day. It took forever, and we barely made a dent in the whole population of calls. The second thing we did is we'd send surveys to our customers. We'd say, hey, we see that you recently called us at Capital One. Can you tell us what you called us about? Yeah, it's kind of funny. But that's another method. The third one is really expensive and intensive, where we just had a lot of servicing agents basically tag phone calls, and we try to see what they talked about. But all of these approaches have shortcomings, and it's particularly Its particular shortcomings are its ability to be real-time and its ability to scale. We never really saw the full picture, and we always had to acknowledge our potential blind spots, that we could only hear a few voices, and we only tended to hear the loudest voices. So to really understand our customer voices, we needed to address these shortcomings, them being not real-time, manual batch sampling, surveys that get really low response rates, have extreme lag, as well as phone call tagging that tended to be expensive, as well as have human biases and errors. So we wanted to move towards something that can scale to the full population, as well as to become real-time. And this is where we wanted to go in our destination. And this is the problem that our data scientists and engineering team helped us solve. So before I hand it off to my colleagues here, who's going to talk a lot more about the how piece, I just want to recap why we care so much about these voices and the data within them. It's because it is a feedback loop. It is extremely rich with data and information that helps us rapidly prototype our products and services that ultimately create value for our customers, and so that they continue to use our products and credit cards. Mark, you want to take it away?
Be happy to do that. Nori. My name is Mark Dickinson. I'm a data scientist at Capital One. I've been there for about 3 years. I joined and I was brought on to work on this specific problem of our voice calls. So I'm going to tell you a little bit about how we cleverly handled that. So I'm not going to say that I'm particularly clever. And in fact, like everything I've done is by using other people's work. We use a lot of open source here in Capital One, and so that's great. And so I like this Sir Isaac Newton quote, which is, "If I have seen further, it is by standing on the shoulders of giants." But since you're not learning from the open source people, you're here learning from me. I'm not going to call myself a giant. So instead, I like this Sam Levinson quote, which is, "Learn from other people's mistakes. Life is too short to make them all yourself." So I'm going to be here today, and I'm going to basically be walking you through a series of mistakes that we made in hopes that you can skip them all and be more clever than I was. So we had this problem. We had millions of hours of audio to turn into text, and we upfront had to make the decision. Do we want to build a system to do this ourselves, or do we want to buy a system from a vendor? There's a lot of vendors that will offer you voice-to-text systems. And then, of course, like I said, we had leveraged some open source systems. And so we sat down and we sort of considered these on three sort of axes. So the first one, of course, is cost. If you're going to build it yourself, there's some time you spend upfront building the system where you're not getting anything done. So you've got higher upfront costs. And usually, because you're not paying for the vendor's margins, you can do this cheaper in the long run for yourself. So it's more upfront costs, lower ongoing costs. Of course, with the vendor, you're paying as you go, so there's less upfront. But in the long run, over time, if you want to keep doing this, you're going to spend more money going through a vendor, probably. Time to market, like I said, you're spending time up front if you're building it. That's time that you're not going to the market. If you buy from a vendor, they can usually deploy you a solution faster than you could stand up your own. One advantage that accuracy has in a build system is you can build the system that does exactly what you want. Any system you buy is probably not going to be tailored to your exact use case. Some of these vendors will only offer prepackaged solutions. Some of the other vendors will tailor a solution towards you, but that's going to take that cost up, and that's going to take that time to market up as well. And so at that point, some of the advantages of buying a pre-built system go away. Whether this decision is even a real decision to you is going to depend a lot where you are in your time frame. If you're in academia, you probably don't have the money to buy a vendor, so your solution is build it yourself. If you're a startup with low employees, but you've got some venture capital, well, you may not have the choice to build. You may have to buy. So this may only really be a real choice for like a mature company like Capital One. That's just something to keep in mind as you go along doing this. So before I get into talking about, like as I said, we built. Before I go into talking a little bit about the actual build, I want to do a poll of the audience. So there's two components that go into building your own system. There's the algorithms you use, the fancy math, And then, of course, there's the data you use to build it. And I want people to vote in the audience. I know audience participation is the worst. But hands up if you think the fancy math is the most important thing, the algorithms you're using. All right, nobody. Oh, we have a couple, one person. You know the answer to this. You want to participate. All right, we had one person. All right, so I think that means I probably don't have to do the other half, but I'm going to do the other half. Who thinks the data is the most important? All right, so most of the audience. That's good. This message is getting out. There's some communities that focus a lot more on the algorithms, and that may be because you see a lot more papers about like, hey, I deployed this new algorithm and I got a 0.2% reduction in word error rate. And you don't normally see like, well, I went on and collected another 100 hours of data and now my sample is better. But yeah, so the answer is data. And I'll give you a little insight why, and this sort of ties back into the model customized for you. So back in 2016, when we were standing up this process, we conducted an experiment. We took some actual calls from our call centers. We made sure that there wasn't any sensitive information, so we could put them onto a public API that Google offered. This was just a sample to do some demonstration. We had superior accuracy, and I put superior with a star there because on our sample, it actually wasn't statistically significantly superior, but it was nice that we were better just even with the raw numbers. The margin of error overlapped for the two. But the following example popped up, which I love to tell people about. So our model produced the following transcript from the customer call, which is what I can do is connect you with one of our account specialists at the dispute department, which was they were calling to talk about like a disputed charge on their card, so that was the correct, that was a more correct transcript. The Google Speech API said, what I can do is connect you with one of your account specialists at the shoe department. And from a statistical perspective, this is actually probably a better decision on Google from the general conversation. If you talk about people day to day, I imagine most of you talk about shoes a lot more than you talk about disputes, whether they be disputes with your credit card or disputes with your friends about who's going to pay the check at the restaurant. But by and large, this is a statistically accurate decision on Google's part for a general model. Of course, we don't get general speech in our call centers. We don't get people calling up and having a conversation about movies or shoes or anything else. They call up and they want to be like, hey, I've got fraud. I've got a dispute. I want to make a payment. So this is the importance about basically saying having data that matches your problem. I'll talk just a little bit about an algorithm for business concerns. So like I said, you see papers and they're all like, I just got cutting edge accuracy. I dropped the performance of some statistical, the Wall Street Journal data set down from the previous record of 5.6 to 5.4. And that makes headlines and everything. But from a business concern, you also have to consider cost. And a lot of times, the fanciest, best model is going to be slower than other models. We did a test of 2 different neural net architectures, so don't worry too much about these acronyms. The time delay neural network was 1% absolute higher word error rate. Or sorry, that should actually say absolute lower word error rate, which is lower word error, it's better. But it was 3 times slower. So in other words, we'd be spending 3 times the cost in order to get a very small gain in accuracy. And for our perspective, that probably wasn't worth the trade-off, and in fact, we didn't go with the slower model. Bear in mind, though, this is concerned with the importance of the decision being made. If for some reason we were trying to use a text-to-speech model to, for example, say whether your credit card application got denied or accepted, we don't, obviously. But if we were, we might really be concerned about that extra % of accuracy, so keep that in mind. It may make sense to use different models in different contexts. If we ever, for some reason, wanted to use a text-to-speech model in, say, credit decisioning, we'd care a lot more about the accuracy, and we'd be willing to pay more money there to get a better result. Another concern is about stability. So if you're training a downstream model, so we have downstream models that look into, say, like, if the customer is making a complaint or not. What is the customer calling about? Those are machine-driven models, and they don't actually understand words the way you and I do. So they just have arbitrary encodings that they turn into features for their models, and really, like, any mapping between these words and tokens would work. So if I went through our transcripts and I swapped, all of the definitions of, if I swapped dispute to shoe, and I did that everywhere, you could train a model that would be exactly as accurate, and the model would just learn that now shoe is correlated with these things instead of disputes, because it's just some future vector. So dropping the accuracy in that sense, so if we trained a model then that fixed that dispute to shoe thing, it wouldn't gain us anything, and all we would have to do is retrain our models. The system we're going to talk about today is actually 4 people. So people actually do care a little bit about what the words mean. They have these preconceived notions that for some reason words mean things, which from this perspective is really hard, but in another sense is really good, because otherwise I don't think people in the audience would be understanding me. And it's, when you make these changes, it's hard to have a big enough sample set to go through and say, all right, all of the models that, or all of the words that all of my downstream models care about, what is all of the impact of when I make a change that might improve accuracy? And so you have to be careful as you do your cadence, whether you're improving an algorithm, whether you're improving your data, to make sure that any downstream consumers you have are on board with this and they're ready to account for those changes. All right. So we went through 3 phases of data collection, and my advice here is to skip the second. So the first thing we did, of course, was we went out and we bought 1,000 hours of public data. We went to the Language Data Consortium. They're a group, collects speech recognition data. A lot of great, Wall Street Journal data set, inner speech data set. There's thousands of hours of various things, conversational calls, recorded on good microphones, good conditions. However, the downside of them, of course, is that they're generic, or some of them were collected for specific tasks, which of course aren't our task, which is credit card call centers. So we were able to build a model with that, and that got us off the ground. But it didn't get us all the way. And so we went to say, all right, now we need data that matches our problem. So the first thing we did is we went and said, okay, well, let's buy it. Let's get an off-site contractor. Let's have them, we'll send them audio. They can send us back transcripts. We can use that for training data. This was relatively cheap as such things go. It turned out to be really hard to ensure quality. We didn't have any direct oversight of the people doing the transcription, and so they'd send us back transcripts, and like the timestamps wouldn't be properly aligned, or they'd skip chunks of the audio, which made it really hard to actually train a good high-quality model for us. Without going into too much of the detail, in most speech recognition systems, including the ones we use, there's the concept of the language model, which is the words people are saying, and the acoustic model, which is the audio characteristics of the sounds that people said. And because of the low alignment between like the timestamps and missing parts of audio, weren't able to really improve the audio model with there, but the language was there, so they'd have the dispute there that wasn't in the public data sets. And so finally what we had to do was we had to bring people on site. We had direct overview of what they do. We could see exactly what they were doing, how they were doing it. We could walk them through the process until they were comfortable with producing the high quality transcripts that we had. So that's one way you can be more clever, is to do that from the start if you need to do that. Talk a little bit here about model development. I'm not going to go too much into how we train this model. We use Caldi, which is an open source toolkit for training speech recognition models. I have like a 2-hour-long deck about how that works, which isn't going to fit into the time frame of this talk. So if you're concerned about that, Caldi is actually, for an open source package, they actually have surprisingly good documentation, which is why we were able to get it off the ground with that reasonably well. We looked at some other open source toolkits, but they either didn't have the features, they didn't have the documentation that made them able for us to pick up and use relatively quickly. It's recipe-based, so all of those LDC data sets pretty much have pre-existing recipes that you can try with different neural net frameworks, different data sets, and you can train up that. When you want to use custom data, of course you have to customize that to make sure that your data matches the format that they accept, and to adapt to any sort of customization that you have for that. We're currently using a state-of-the-art, it's a hybrid hidden Markov model and deep neural net with a recurrent neural net language model rescoring. Like I said, 2 hours about that. If you want to hear that, you can ask me, or you can go to the Caldi documentation. And the great thing about it's open source. It's currently actively developed, and it's updated with new capabilities or performance improvements, which of course, as I mentioned, you do have to take the business concerns in there. Sometimes you'll get a performance improvement, and it'll be real but marginal, and so you have to ask yourself the question, like, is it worth the impact to our downstream consumers to go through and roll out this change that they're going to have to take into account? So we do updates, but not as frequently as they do. Okay, so we trained a model. Great, we've got it. I can run it on my local machine. I can give you a call. It's pretty fast. It's faster than real time. But as previously mentioned, we get 1,000 days of audio per day, and it's not 1,000 times faster than real time by any means. So we need to deploy this on a lot of machines. Where do we want to do this? We could have stuck it in one of our data centers, but that's not the way we wanted to go, because we're trying to move out of our data centers and be agile and towards the future and cloud-based. So we chose Amazon Web Services. We set up a system that takes through, it responds dynamically to call volumes. As will probably surprise nobody, we don't get too many calls at 2 o'clock in the morning. We get a lot of calls at 2 o'clock in the afternoon. So we have machines that scale up as more calls come in. They do that transcription. When calls stop coming in, machines scale down. We've got a output streams to downstream models as well as downstream analytical tools. So that's great. And now to talk about how we can use this all quickly for our analysts is Nori.
Thanks, Mark. Hi, everyone. This is Nori. I'm the tech lead on the engineering team. I need a clicker. So now we are able to work with these text data as opposed to audio files, and that was really a game changer. However, imagine opening all these millions and millions of text files and reading through them in order to run all this analysis to get insights is just not a humanly possible task, right? So what we realized is we needed the capability to be able to search across all the transcripts, filter them, classify them, visualize them in order to get to the insights much faster. And that's exactly what we built. So we built this search engine platform to do it, and our search engine can run various type of queries. In addition to the transcripts themselves, you can search across the metadata that we have, such as call reason, the duration, as well as account ID. So we could run a search such as like, I want to find transcripts that had to do with the call that took more than 60 seconds, where the customer was talking about making a payment on the website, on our website, against our venture card balance. And that's pretty simple for us to do now. And we also support more advanced queries, such as fuzzy and proximity match for querying similar words and phrases. And of course, we support regular expressions. You can also boost certain contexts in our phrase to increase the relevance of certain words in a phrase. And if you are a more technical, advanced user, then you can also build out inline scripting, which is something similar to like the traditional relational databases stored procedures. So how do we do this? How did we build this platform? We built it using microservices architecture, which enables us to select the right, most appropriate technology for each feature that we build out. And there's a lot going on in our tech stack here, but today I'm gonna zoom into Elasticsearch, which is the core of the search engine. How many of you have heard of Apache Lucene? Okay, some of you. It's the most widely used Java library to build search engines. Essentially what it does is it gives you the mechanism to build out indices of documents and text and enables you to quickly retrieve them back later on. So why aren't we using Apache Lucene? Why are we using Elasticsearch? It's because Elasticsearch is built on top of Lucene, and it enables us to leverage Apache Lucene in a much more fast and easy fashion. But before diving into the details of Elasticsearch, I want to talk about, or just review the basics of the inverted index, which is the data structure that a lot of the search engines uses. So let's say we have these 3 documents that we want to index. Documents are ID'd as 1, 2, 3, and it contains the text, I am your father, you're talking to me, you had me a hello. And what we would do is first you do some basic text processing, such as lowercasing all the text, removing punctuation, and splitting words. And after splitting these words from the text, then you can take those words and then use them, map them as terms to documents, as you can see on this inverted index table here. And I don't know if you noticed, but these terms are also sorted in the dictionary. So if you want to search through them and get to a specific term and scan them, you can get to it really quickly. And then once you can get to the term, you have other metadata, such as in this case here, I have the frequency of or the occurrences of the text that happened in all the documents. Or sometimes you can have like a position in the document to help with optimizing your search better. So let's say I want to search for phrase venture card. What you would do is run a query individually for both of them, and you take the results and take the intersection for, let's say, when you're doing an end query, or you can do a union of the results for all queries and aggregate the results and get the final set of the documents and get your hit results. So for more advanced queries, obviously this is gonna be a lot more elaborate, but the concept is very similar. So as you can see, the terms dictate the speed of searches. And I wanna just quickly go over some of the samples of term transformations to show you guys what are some techniques that people are using to build their indices optimally for efficient searches. So let's say I have the word great and I want to do a search by suffix. Let's take EAT. So what you could do is reverse the word great and index name as TAERG, and that way you can actually search for TAE to do the suffix search. For substring search, you use these splitters to split the terms into smaller terms called n-grams, and what it does is what you see up here. For geographical coordinate points, you can convert these coordinate points to a geohash, which essentially what it does is it shrinks the length of the string, so you can essentially optimize the search that way. And for finding spellings that are close to the input to achieve a feature like did you mean, you can use what's called a Levenstein automation to build an index for effectively traversing the dictionary, which I have no idea how that works. It's like a magic to me, so I can't explain it to you exactly how that works. But that's available in Elasticsearch. So let's go back to Elasticsearch. So with Apache Lucene, to specify all those what we just talked about and to indicate a data type for a specific keyword, or picking different tokenizers or analyzers to split the phrases into terms, you have to do all of it in Java programming language. So you have to be a decent programmer for you to be able to write a code that does all that for you. But in Elasticsearch, it's all configurations. It requires no writing code. So it's very easy to get started. And in terms of just standing up the search engine on itself, there's no code writing involved on the server side. And that's one of the first reasons we chose to use Elasticsearch, because it was really easy to get started. And in our architecture, I mentioned microservices earlier. So we have all kinds of microservices everywhere in Capital One. And these microservices has to talk to each other and grab information from our search engine. So as you can see, these microservices can live in different nodes, different machines, and different environment, different virtual private network. So it would be really difficult for these microservices to get access to like a file system that the Apache Lucene has, right? So what Elasticsearch does is, like I said before, embeds Lucene into like a web container and then expose the usage of it over HTTP. So it makes it very easy for these microservices to orchestrate and interact with the search engine that way. So second reason is that Elasticsearch is microservices friendly, and that's why we use it. So when you deploy a Elasticsearch, you deploy a cluster. And inside the cluster, you could have multiple nodes that could be spread across multiple machines. And that way, and then as you add more node and more node, what you get is more hardware. So you get more CPU power, you get more memory, you get more disk space, and that's how Elasticsearch actually enables us to easily and quickly scale Apache Lucene instances. And so how does Elasticsearch do that? There's this concept terminology called shard. Essentially, what a shard in Elasticsearch is a Lucene instance. And it's spread across a single index. And a bunch of these shards essentially makes up a single index. So that's how Elasticsearch is able to share or split the resource that requires for a massive index to be spread across multiple machines. And there's also another shard type called replicas. They're just a copy of the primary shards that we just talked about. And what that does is it gives us data redundancy. So let's say node 1 or machine 1 all of a sudden goes down. Do we lose the entire service? No. You can see that node 2 or machine 2 has a replica of shard 1 and 2. So we can continue to operate without having a downtime. And when you actually have two nodes, or node 1 and node 2, up and running at the same time, then let's say a client requests multiple queries at the same time against those shards, we are able to parallelize the execution of the read against these shards. So you can increase the performance of getting back to the clients by parallelizing that execution. So this all feels like very complex to understand and configure, but Elasticsearch ships with very sensible configurations already. So usually you can just fire up the server and then get started on using. So we have these great 5 reasons why we're using Elasticsearch, but there's actually more. There's a graphical user interface called Kibana for Elasticsearch that enables you to very easily explore all our data. And within the same Kibana graphical user interface, you can create a bunch of different charts and visualizations and dashboards as well. And there are even more that I want to talk about, but my time is limited here. But essentially what it comes down to is that Elasticsearch was able to provide us the speed to get the search engine up and running very quickly and getting our business analysts to get to the insight really fast. So that's my talk. Thank you. Yes. Yes. Where are you hosting your Elasticsearch? AWS or we are hosting it inside AWS. We're not leveraging the Elasticsearch AWS service, but we are standing our own EC2 instances and deploying themselves using automation. Yep.
All right, thanks, Nori, for helping us go faster so that our customers can go even faster. can't keep up with this guy. So the next part is the last and fourth part of the Capital One talk. My name is JayZ, like the rapper. I am from Brooklyn, and we are going to rap today. Anyone here want to join in on the rap? Raise your hand. We have 1, 2, 3. Any others? I know some of our team were going to join in as well.
We have 3 more microphones.
Oh, that's true. You can come up here and participate as well. So stay tuned. And now that we've taught you how to be rich, clever, and fast, the last part is how to get famous. And I think that some of you already are famous, so you can confirm if this advice is true. But we want to make your products famous among your customers and or also internally at your company. So solving pain points is a surefire way to help you get famous. And since so many of you are already famous, I think you already know that. I wanted to talk about the Lego pain assessment tool. So that's what nurses use when you go to the emergency room. They'll ask you, how much pain are you in? If you're at pain level 2, does that say mild pain? You could be mistaken for smiling. Like, I don't know why you came into the ER today. Maybe you just need an aspirin. There's a workaround. There isn't an emergency per se. So you might not get to see the doctor that day at all. But if you score yourself as 10, worst possible pain, I think there are these furrowed brows and like open mouth agony happening at that Lego face, then you'll get to see the doctor. Like you might see the cardiologist in an hour because they'll think of you as a high-risk case. And so that's how we like to build products as well. We like to build products where there's no workaround. Aspirin is not gonna fix like the furrowed brows in this case because you don't even know what's going on. That's why you're at the ER and the nurse is gonna let you in immediately. And that's what we did. So as the rest of our team has mentioned, we have 1,000 days of phone calls every day. And it is literally impossible to analyze all of those phone calls if you're gonna have to re-listen to them. There was no existing workaround, and everyone at the company wants to help the customer, but they couldn't listen to all those calls. So that's what our team did to get famous, is we created this search engine to search the text in the voice-to-text pipeline so that we could understand what our customers were asking of us. And we got really famous. So I'm gonna close each of my slides with a rap, and the rap is on the screen. So you all, and maybe some of you, I invite you to rap along, and I'm gonna go really slow so we can all get to the beat. All right. If you got problems, I feel bad for you, kid. I got 99 problems, but doing right by customers ain't a problem. Solving for 2, mild pain, would be a problem. 2 down here. Solving for 10, worst possible pain, ain't one of my 99 problems for making my product famous. All right, next time, you'll join in, right? So we got famous. And then we ran into this new problem. Scaling became a problem. And we realized that there's actually a really dark side to fame. So you'll hear JayZ, myself and the other one, and Beyonce and all these other people talk about the dark side of fame. And you're like, that doesn't seem like, that's like a nice first world problem. They complain about losing privacy. They've lost all freedom to go to the supermarket. There are paparazzi everywhere. And you're like, that's a good problem to have. I wish I had that problem. So if you're solving for pain points at level 10, I promise you'll get there. You'll get to this problem. So what happened is that we started with our fraud team. our internal product was powering their ability to help hundreds of customers be less stressed about fraud notifications that they got. And then another team, the phone agent team, used our internal product to help hundreds of thousands of customers pay their bills faster via our phone IVR automation. And then the credit card team used our internal product to give higher rewards points to millions of customers. And that's when it all started. So I get all of these teams and additional teams coming to us, well, me, emailing me, like, where's my feature? Where's the feature that you promised you could build for me? I needed it yesterday. Can I see your roadmap? What's your commitment to timelines? And if you're a product manager, you've released things in market, this can be really stressful when everyone wants something different. So we decided that we would continue to honor our customers, and we prioritized by millions of customers impacted, millions of dollars saved, and really focus on the high leverage, high impact problems. So some problems, although they were by very loud and vocal people in the company, they only impacted a couple hundred customers, and they only saved us like a couple $100,000. So prioritize by impact, and everyone will know. It'll be transparent. So you won't get, these angry, insistent people, and your paparazzi will have a better idea of why you're prioritizing them, maybe not first, but in the middle. And then all these people had teams of teams who wanted to learn how to use our product. So we'd be in headquarters, and people would come up to me, and they would say, oh, I'm going to put an hour on your calendar to get trained on this product. And I'd be like, and then I would start hiding from people in the office and wearing like hats and sunglasses, because I get 4 hours of calendar invites every day from people who hadn't even asked me, from people who just like found out about us through the rumor mill, through all those other. So it's really helpful when you can scale your trainings. And Nori's team has been amazing. They're recording videos of all the trainings that we've been doing manually, so that it's automated and self-serve, and people can get the information without adding all these additional meetings to your calendar. So I'm going to summarize this slide with a wrap. This is your second chance to be a rapper. Don't miss out, right? I'm going to count to 3. 1, 2, 3. But I got teams. Why haven't you built my feature yet? And I got hours of meeting requests every day. Train me, help me. But prioritizing by impact and automating education, making the dark side of fame ain't a problem for making your product famous. All right, we've got one more opportunity. This is my last slide. So now you're famous. Now you learn how to deal with the paparazzi. You understand you've lost your freedom and your privacy. You're there. And you've won the right to build teams to continue to add value to your customers and your company. And so now recruiting is a problem that we like to have. And we'd love if you talk to us after. We're recruiting for all of our job families: business analysis, data science, tech, product management, Scrum, and design, all of the above. And I think, Mark, you're going to do this rap with me, right?
I suppose.
Okay. And anyone else?
Get a guest rapper on the track.
Anyone else who wants to join us?
We got microphones. That's great. We should have gotten Alexa to sponsor this.
All right, so
or
what's
Google
that?
Voice. I don't know if there's nothing about shoes in the rap though. So.
All right, on 3. Okay, 1, 2, 3.
Half a million callers every day were asking us, and the total sum of all the data was massive. Thus, product tech, data science, business analysis work together making product. Just to answer
this.
We rehearsed this, whether you believe us or not. I got 99 problems, one of which is this rap, but helping customers ain't one. If you're having job problems, I
then
feel bad for your
for
son.
anyone. I
got
got 99 problems.
Helping callers ain't one. Hit me up after the talk if you're
if
interested in working for Capital One.
All right. Thanks, everyone. So that's the conclusion of our talk. Rich. Timmy, will you stand up for Rich? Mark, you're already standing for clever. Nori, stand for fast and famous. All right, millions of dollars in searching customer call transcripts and machine learning insights. And we're recruiting, so this is our recruiting website, CapitalOneCareers.com, product innovators, and you can also email me or talk to any of us after the talk. All right, thank you.
We have some time for questions. It looks like we actually have a couple